Hello everyone, welcome to this video. In this video, we'll be discussing about the eighth property. It states that if K bar is a normal subgroup of G bar, then phi inverse K bar is a normal subgroup of G. Remember the diagram here, right? I told you that we have some group G, we have some group G bar, right? And we have defined a mapping from G to G bar, which is a homomorphism. Now in this group G bar, we are taking some subgroup which we are naming by K bar. Then we are taking some inverse image of this K bar over here. So this inverse image would definitely lie where in it would lie in G bar. So what is this? This is phi inverse K bar. So now we are saying if this K bar is a normal subgroup of G bar, then this inverse image, which is phi inverse K bar, is also a normal subgroup of G. This is the result. Now we are given K bar as a normal subgroup of G bar, right? So therefore, by the normality test, if you take some element from G bar, which is say phi of x, and you take some element phi of k from K bar, right, then phi of x, phi of k, phi of x inverse would belong to K bar. Why? Because it is given to be a normal subgroup of G bar, right? Now notice that whenever we say we use this notation here, x phi inverse of K bar, x inverse, this element has this form phi k x inverse, where phi of k belongs to K bar. So any element from here would be of this form k, where we have this condition on k that phi of k would be equal to K bar, correct? So this is the notation here. So why I am telling you this notation? Because we wanted to prove this to be a subgroup. So that means we have to take some element from G here, and its inverse would also belongs to G. So here we should take some element of phi inverse K bar, right, in order to prove this to be a normal subgroup. Thus, to prove that phi inverse K bar is a normal subgroup of G, right, is a normal subgroup of G, we have to prove that x inverse belongs to phi inverse K bar, where phi of k belongs to capital K bar, right? So in what does it mean to prove that x inverse belongs to phi inverse capital K bar? It means that we have to prove phi of this entry is present in K bar, right? This is the other way we can write it down by the definition of how we have defined phi inverse K bar. Okay, so what we do, we consider this thing phi of x k x inverse and see if it is present in K bar or not. So let's consider phi of x k x inverse. So by the properties of homomorphism, because phi is an operation preserving mapping, so therefore we can write it like this: phi of x, phi of k, and phi of x inverse, right, like this. Now you can again write phi of x inverse as phi of x inverse, whole inverse. Now from the equation 1, you can clearly see that we have this present in K bar. Why? Because K bar is a normal subgroup of G bar, hence this is present in K bar from equation 1. Therefore, if this is so, what does it mean? It means that phi of x k x inverse belongs to K bar. Then by the definition of phi inverse K bar, this element phi x k x inverse is present in phi inverse of K bar by the definition. And this is what we wanted to prove, that this phi inverse K bar is a normal subgroup of G, correct? Not G bar, G, by the normality test. So I hope you understood this property well, right? Well, that is it for this video. Thank you for watching.